Hello everyone, welcome to the SWAM NPTEL course on mathematical geophysics. We continue with the module number 8, Data Driven Analysis in Geophysics. This is the lecture number 5, Data Driven Methods in Geophysics. In this lecture, the concepts which are covered are related to the data driven methods in geophysics. First, we will look into the concept of singular value decomposition. Next, the singular value decomposition method. The third component of this lecture is the principal component analysis, followed by proper orthogonal decomposition. Finally, we will look into the geophysical applications of data-driven methods. So let us begin. The singular value decomposition is the powerful linear algebraic tool which is used for factorization of data. Since we have seen that geophysical analysis and measurements uses data obtained from various instrumental measurements, the representation of this data set in proper representative manner is of utmost importance for its clear interpretation. The singular value decomposition also plays a critical role in various other fields of data-driven science such as physics and engineering. The singular value decomposition is suitable for data-driven analysis in geophysics. By data-driven analysis, what we understand is that we have a set of data, and without using any further theoretical models, we obtain the underlying structure or the representation of this data into a simpler forms. Now, this is primarily done from using the data itself rather than any other theoretical equations, models, or other factors. The data-driven analysis is primarily done using singular value decomposition, which is a matrix-based method. Now, matrix method is a representation of a set of data in a structured format. All of us know what does a matrix look like. The singular value decomposition decomposes a matrix into three components. For example, let us consider a matrix as shown in equation 1. We have the data sets arranged in the matrix. These are the data sets. How are these data sets obtained? Let's say we have a domain represented by the Cartesian coordinates x and y. The sample data can be obtained at the grid nodes. Now, this would give us a matrix. A n cross m, where n is the number of rows and m is the number of columns. Now, the total data set comprises of n cross m or nm numbers. Thus, this can be represented as data sets as given in this diagram. X1 represents the data which is obtained from m equals to 1. This data is kept in X1. The second column is represented by x2 and so on till xm. The last column is represented by xm. This gives us a complex matrix of C n cross m. This is one way to arrange a large data set in a matrix form denoted by capital X. In case where n is greater than m, this indicates tall skinny matrix, which means that one of the dimension, which is n, which is the number of rows, is much larger than the number of columns. While the opposite case, n much less than m, indicates short fat matrix. The first one is tall skinny matrix, while the bottom one is the short fat matrix. We can also look into an alternative data scenario. Now suppose instead of this space domain x and y, we can have a time series data. For example, we have the x along the column and time along the rows. At a particular time, we have all the data along x arranged in one column. Thus, the columns represent various instances of the data at various times, called snapshots. Thus, the columns are snapshots, and m is the number of snapshots. So, here we have seen how we can arrange the data set which are obtained from either spatial data or spatiotemporal data into a matrix form, which will later be used for further data-driven analysis using SVD. Now, coming to the process of the singular value decomposition. The singular value decomposition decomposes any complex matrix into three matrices. This is given by capital X equals to U sigma V transpose. Here, U and V are unitary matrices with orthonormal columns. Note the dimensions of the U and V matrices. U is an n cross n matrix, while V is an m cross m matrix, where n and m are rows and columns of the original data set. These matrices have orthonormal columns, which means that the individual columns are linearly independent from each other and have a net magnitude equals to unity. The middle matrix, that is sigma, is a real matrix. It consists of non-negative entries on the diagonal only. The off-diagonal entries are 0, and hence sigma, which is n cross m in size, is a diagonal matrix. The singular value decomposition can be represented in diagrammatic form as given in the adjacent diagram. Here, X is the dataset matrix, is decomposed into U matrix, which is given by this matrix. The sigma and V matrices are also shown. Note the sizes of these matrices. U is n cross n. Now, in this particular case, it has been assumed that n is greater than m. Thus, the U matrix is larger compared to the V matrix. Both are square matrices. However, the sigma matrix is a rectangular matrix. Now, since n is greater than m, the sigma matrix has a complete submatrix composed of 0 entries. These diagonal entries are non-zero. The lower submatrix is completely 0 entries, while the off-diagonal entries are also 0. Now, from here, we can proceed to represent this in matrix form as equation number 3. Note that the sigma matrix can be written as the combination of the diagonal part and the 0 part as given here. Sigma hat represents the dark shaded region of the sigma matrix, while the 0 matrix is the lighter shade representative respectively. Now, using this notation, we can write x equals to u sigma v as U is decomposed into two submatrices u hat perpendicular. Sigma is decomposed into two submatrices sigma hat and 0, while B star is as it is. Now, U hat is the region of U matrix shown in dark region, while the lighter part is given by U hat perpendicular. In vector notations, the columns of U hat perpendicular span a vector space that is complementary and orthogonal to that spanned by U hat. This is because n is greater than m. Thus, only the part of m which is in n that is in the darker region. Thus, the columns of U are also called the left singular vectors of X. And the columns of V are called the right singular vectors of X. Now, since we have a U hat matrix or submatrix in particular, and its columns are spanning a vector space which is orthogonal, then we have these columns of U hat vector as a basis vector for an entire vector space, which means we can construct any vector by a linear combinations of the columns of U hat. These generalized vectors are nothing but the original data set. In fact, the singular value decomposition is performing a segregation of the various modes which are in the generalized data vectors into U hat columns. The generalized data is also obtained from a combination of the modes. Now, these modes are the simpler forms of the data which we are interested in, and that can be obtained from U hat vector. Now, the diagonal elements sigma hat, which are in n cross m complex matrix, are known as singular values. These singular values are also sorted from the largest to the smallest in magnitude. the rank of the matrix X is equal to the number of non-zero singular values, which is essentially the number of linearly independent vectors which can form the vector space spanned by the columns of the data matrix capital X. Now, using the singular value decomposition method, we can understand the concept of principal component analysis. Now, principal component analysis is a dimensionality reduction technique. What do we mean by dimensionality reduction? Dimension is a form of representation of the data as the number of independent coordinates or the number of independent degrees of freedom in which the data can be represented. For example, let us consider the phenomena of mantle convection. It depends on various factors such as the temperature, pressure, properties of material, etc. All these components contribute to the mantle convection, and each of them can independently affect the nature of mantle convection. Now, these form the various degrees of freedom on which the mantle convection depends. Thus, the data set, for example, fluid flow data from mantle convection, can be analyzed in various degrees of freedom. Now, here we have to reduce the dimensionality. In mathematical terms, it is useful to reduce the dimensionality for better representation of data. We will consider a simpler example for the analysis shown here. The principal component analysis, in definition, transforms high dimensional data into lower dimensional form. The principal component analysis transforms high dimensional data into low dimensional form. It preserves most of the significant features of the original dataset, while some negligibly important features are omitted. Now, the principal component analysis relies on the singular value decomposition to find out the most important or significant features which it can retain, and to omit the not so essential features. Now, coming back to the singular value decomposition, note that we have understood that the matrix U hat here has the columns as the various modes. Now, each individual mode, which is essentially column of U hat vector, represents the significant feature of the data, as significant as the singular values. Now, since the singular values are sorted from largest to smallest, the first column of U hat vector is the most significant. The second column of U hat vector is the next significant. In principal component analysis, it is the requirement to retain the first few columns of U hat as the most significant features and omit the rest of the data features, which are very less significant. The computational algorithm for implementation of principal component analysis is shown here. For example, we consider the matrix X, which is the data matrix. We compute the row-wise mean of X, which is essentially taking the entire row and taking the average. This gives us Xj, which is 1 by n summation of I equals 1 to n Xij. Recall that here we have n equals to 1 to n equals to n. For each individual column, we would be averaging over this entire column. The average data obtained from this column would be represented by Xj. Now, this is performed for all the columns. This gives us the mean matrix x bar, which is equals to 1 vector, that is the unit vector, into x bar, which is obtained from equation 4. Subtracting mean from x, we obtain the mean removed data matrix. The mean subtracted data essentially moves the data distribution to be centered at the origin, such as shown in this diagram. For example, if the raw data would have been located such as subtracting the mean from the original data would move the data set to be centered at the origin. That is the function of mean subtracted data. Now we compute the covariance matrix. The covariance matrix is given by C equals 1 by n minus 1, B transpose B. This is the covariance matrix. Now the first principal component of this covariance matrix is U1. This U1 is given by equation number 8, which reads the maximum argument of U1 star B U1 over modulus of U1 equals to 1. Now equation 8 can be represented in terms of matrix calculation as the eigenvector of B star B. U1 is the eigenvector of B star B, which has the largest magnitude. Also, U1 is the left singular value of B corresponding to the largest singular value. Essentially, U1 is the first column of the matrix U hat. This first column of U hat is nothing but the U1, which is the most important component of this data and hence is known as the principal component. Now, for example, if the original data set is shown as here, the principal component would mean this direction, because this data set is depending upon two axes. Let us say these are x and y axes, and the distribution of this data set is such that one of the axes is more important than other axis. Now that axis is neither x-axis or y-axis. It is the axis which is passing through the entire data set. That is this axis. The perpendicular to this axis is this axis. So instead of choosing x and y as the independent degrees of freedom, we can choose this principal component as the axis to represent this data set. Now, if we denote the principal axis as P1 and the second principal axis as P2, which are the principal components of this data, then we can represent this data in this axis. Now, One can easily distinguish the importance of these axes P1 and P2. The P1 axis is considerably more significant than P2 as most of the data sets have the alignment along P1. P2 is the second most significant axis. But if we look at the original data form, which is depending on x and y axis, each of these axes is equally important as the spread or dependence or sensitivity of the data set to each of these axes is equivalent. These are the ranges of x and y axis in the original data set, which are approximately equal. Hence, the significance of x and y axis of the original data set is equivalent. However, converting this into the principal component form, we can easily see that the principal axis 1 has much more significance than P2, which is much less. Thus, one can now represent the entire data set using P1 only and neglect P2. Thus, we have transformed the degrees of freedom number from 2 to 1. The 2 degrees of freedom in the original data sets is xy, while the single important degrees of freedom in the principal component axis is P1 only. This is the dimensionality reduction, that is, reduction in the number of dimensions from 2 to 1. Now, let us look into the proper orthogonal decomposition technique. The proper orthogonal decomposition technique relies on the singular value decomposition method to obtain the most significant data patterns in a complex data distribution. Inherently, POD is also related to principal component analysis and SVD. However, it is useful for time-dependent and spatially dependent data. This is used in the context of dynamical systems. POD uses singular value decomposition method to represent the data set capital X. Thus, we have the data set X decomposed into UK, sigma k, and V star k. The K subscript denotes the restriction of the decomposition to the K most energetic modes. These most energetic modes are nothing but the economic version of the singular value decomposition. The economy version of singular value decomposition only takes in the gray shaded area from the general decomposition. You can see that the capital X economized can be represented by only the product of U hat, sigma hat, and V star. Here, the U star, star, and 0 matrices are omitted. The number of columns in these are k. This is the economy SVD. The economic SVD is used in proper orthogonal decomposition to find the most dominant k modes, which are energetically the maximum. Note that in principal component analysis, the energy maximum is not considered. The principal component analysis is a general technique where the dimension is reduced, while POD is useful to obtain the most energetic modes in the dataset. Essentially, POD represents the dominant structures or patterns in the data. It can also indicate how each of these patterns evolve over time. It also indicates the relative importance of each mode. Now, let us consider these diagrams, which are the proper orthogonal decomposition of real geomagnetic field datasets. Now, consider these diagrams where the latitude and longitude of the global distribution of radial magnetic field is shown. The radial magnetic field is the R component of the magnetic field vector B. We have the longitudes from left to right and latitudes from top to bottom. The central line indicates the equator. This diagram is essentially the hammer projection of the globe. Now, this projection is useful to represent the entire globe data on a flat surface. Having understood the mapping, let us focus on the pattern of the magnetic field. One can see that the magnetic field or the radial magnetic field is positive on the northern hemisphere, while negative in the southern hemisphere. Now, this is very complicated distribution. Upon application of the proper orthogonal decomposition, we obtain two of the most energetic modes as shown here. The most energetic mode indicates that the most significant pattern in the data set is given by the mode 1, which is essentially a dipolar structure, indicated by the spherical harmonic Y10. As we know, the Earth's magnetic field is dominantly dipolar in nature. That is also indicated by the mathematical analysis of proper orthogonal decomposition, which is truly remarkable. The second mode is indicated by an oscillatory, spatially oscillatory mode, which is given by POD mode 2. This feature shows that the oscillatory patterns or spatially periodic patterns near the equator form the next most energetic dominant mode of the radial magnetic field. These modes arise from the patterns which are distributed close to the equator. Thus, from such type of analysis, we can understand that the radial magnetic field has two major patterns. One is the north-south dipolar distribution and the equatorially spatially periodic distribution. This diagram represents a typical decay of the singular values in the POD analysis. The most energetic and the significant data structure is shown as mode number 1. The significance of the individual modes gradually decay and become lesser and lesser as the mode number m increases. In geophysics, various applications of the data-driven methods are prevalent. First, let us see the seismic data processing. In seismic data processing, SVD is used to separate coherent signals from random noise. The seismic data matrices are decomposed to obtain the dominant singular values. These dominant singular values corresponds to particular and significant seismic events. The smaller singular values denote noise. In geophysics, various ill-posed inverse problems can also be solved using the technique of singular value decomposition. The singular value decomposition regularizes these problems by decomposing the model space and selectively retaining the significant singular values. This reduces the numerical instability and makes the ill-posed problem a well-posed problem. In today's scenario, where machine learning and its application are inherently becoming more and more important and significant, the geophysical exploration also makes use of such applications which are based on singular value decomposition and principal component analysis. The features such as dimensionality reduction and extracting of essential features improves the models and performance of the interpretation. This helps in mineral prospective mapping and subsurface classifications. The coherent seismic reflections are also separated out using principal component analysis in seismic studies. The reconstruction of the data set using the most important significant modes only enhances the signal to noise ratio. Large-scale geophysical inversion problems, such as those involved in gravity inversion, magnetic inversion, and electrical data inversion, utilize proper orthogonal decomposition to reduce the number of model parameters, which is essentially similar to dimensionality reduction of the data. This results in a smaller set of dominant modes, which represent the subsurface structures more accurately and clearly. Thus, we come to the conclusion of the present lecture. First, data decomposition. SVD is effective in separating signals from noise by decomposing the data into orthogonal components. Second, the noise reduction. The filtering action of singular value decomposition enhances the quality and the signal to noise ratio. This clarifies the geophysical signals. Third, the dimensionality reduction. The technique of principal component analysis simplifies large geophysical data sets and reduces the degrees of freedom. This helps in identifying the most important contributing factors for the geophysical phenomena and its control. Next, we have the noise attenuation. Noise attenuation is achieved by principal component analysis effectively. This enhances the data quality. Finally, proper orthogonal decomposition helps identify the most energetic modes. It helps detect the significant data patterns and further enhances the interpretation and geometrical representation of these data sets, which are useful in geophysical applications. Thus, we come to the conclusion of this present module and this lecture series. One can go through the following references and the various references which we have discussed throughout this lecture series for obtaining greater understanding in the subject of mathematical geophysics. I thank you for your patience and attention throughout this course and hope this would be very useful and relevant for your further understanding of mathematics as well as geophysics and the symbiotic relationship which exists in between the both that enhances our understanding of the Earth and planetary systems and in nature in general. Thank you very much.